Hello, my name is Matthew Bertrand. This is my chemistry teachback for the Princeton Review, where I will be talking to you about the atomic structure and the periodic table.
Now to begin, as you can see, I have drawn a rough sketch of the periodic table of the elements. Now this will be important when we go over some common atomic trends. So to begin, as we move horizontally across the rows from 1 to 8, we have what are known as the periods. And as we go down vertically to 1 to 7, we have what are known as the groups. If you look down here, I have taken the element carbon out of the periodic table and made a larger version of it just to clarify a few things. The first thing you may notice is the large letter C in the middle. This represents the atomic symbol for carbon, which as you can see is C. Now, every one of the elements has its own unique atomic symbol, which helps us to distinguish which element is which when we are talking about them. This number above the atomic symbol is known as the atomic number. Now, the atomic number lets us know the number of protons, neutrons, and electrons within the atom at a neutral state. For example, the atomic number for carbon is 6. Carbon has 6 neutrons, protons, and orbiting electrons. The number below the atomic symbol is known as the molar mass or the atomic weight. Now, this mass number is the sum of the neutrons and protons. Atoms of a certain element with different numbers of neutrons are called isotopes. So, for example, carbon or carbon-12, which is the most common form of carbon, has 6 neutrons and 6 protons. However, carbon-14, one of its isotopes, has 6 protons and 8 neutrons, and this greatly increases the atomic mass. So as you can see here, I have drawn the atomic structure of carbon. In the center, this is referred to as the nucleus, which has the neutral neutrons and the positively charged protons. And as I said, in these rings circling around the nucleus are known as the electrons, which are negatively charged. Now, in order to understand why there are different rings and the electrons aren't all circling one ring, we must then understand the quantum numbers. In regards to quantum numbers, these are referred to as the position of an electron in relation to the nucleus. So to describe these positions of the electrons, we use shells, subshells, orbitals, and spin. Shells, which we give the letter N, typically referred to the group number that the element falls on. So for carbon, our group number is group 2. Therefore, we would give carbon a shell N value of 2. The shell is what determines the electron's average distance from the nucleus. Therefore, electrons in shells with higher values are farther away from the nucleus. Next, we go to subshells. And subshells, they describe the shape of the electron orbital. So for example, group 1, which would have an N value of 1, would have a subshell of S. Now, subshells, given the letter L, would refer to an S value of 0. However, if we had a shell value of N equals 2, as you can see, we have subshells S and P. Subshell S would still be given a value of 0, however, subshell P is given a value of 1. Moving along, we get to orbitals, which are denoted by an M with a subscripted L. Now the orbitals, which are also known as the magnetic quantum number, describe the orientation of the orbital in space. For example, if it lies on an X, Y, or Z axis in a 3D grid. So, to describe this, the S subshell, which equals L0, has one orbital, which we also give a 0. However, the L subshell P has 3 orbitals, which we give -1, 0, +1. Finally, we have spin, which is denoted by an M with a subscripted S. Now, each orbital can contain 2 electrons, shown in this fashion, one pointing upwards, one pointing downwards. This tells us that each electron within the orbital has one positive charge and one negative charge. Therefore, we always give our spin values a plus or minus 1/2. To explain this more clearly with our carbon example, if you can see, carbon, as we said, is in group 2. Carbon's in group 2. Carbon's N value is therefore 2. Carbon's L value, or subshells, are S and P. Because of this, its S value, as we said, has a 0, and its P value has a -1, 0, +1, or +1 value. And each of these have a spin value of plus or minus 1/2. So when we draw it out, we show, due to the 6 electrons in 1s, we have 2, 2s, we have 2, and 2p, which are the 2 left over, we have 2 as well. Now, as you may notice, the orientation of these are different, and this is due to Hund's rule. And Hund's rule basically says when an electron is added to a subshell, it will always occupy an empty orbital. That's only if one is available. So basically, S can only occupy two electrons at once, but P can occupy 6. But since we only have 2 left over, and there are all these empty spots, each electron wants to occupy its own orbital. Next, we will be discussing a few common of the atomic trends found on the periodic table of elements. So to begin, we'll discuss the atomic radius. So the atomic radius, typically, as we go across the period, left to right, we find a decrease in the atomic radius. And this is due to the increase in the effective nuclear charge. Conversely, as we go down the groups, we find an increase in the atomic radius, which is due to the addition of a new energy shell, as we had talked about previously. So, to understand this, here we have lithium and here we have sodium. Lithium and sodium are both found in the same period, period 1. However, lithium is in group 2, sodium is in group 3. Because of this, lithium only has 2 energy levels. However, sodium has 3. This extra energy level increases its atomic radius. Next, we have ionization energy. Now, ionization energy essentially is the energy required to remove an electron from an atom. So it's less likely for an atom to give up an electron, the more energy required to take that electron away. So as you may have guessed, this would show an opposite relationship to the atomic radius, as we can see here. So ionization energy increases in this fashion. So a greater ionization energy when we go up the group and across the periods. Similarly, electronegativity, or the ability of an atom to attract electrons, follows a similar trend. This is because electronegativity is how strongly the nucleus of an atom attracts the electrons of another atom in a bond. So more simply put, Here we have lithium and here we have fluorine. Now lithium and fluorine are both found group 2 on the periodic table. However, fluorine, since it's in period 7, has 7 valence electrons, which means electrons in its outermost ring. Because the fact that atoms are most stable when they have 8 electrons in their outermost ring, there is a much greater force on this lone electron being attracted towards fluorine than it is being attracted towards lithium. Because of this, the most electronegative atom is fluorine, with a value of 4 on the Pauling scale. One final important atomic trend is known as electron affinity. Now, more simply, electron affinity is the energy released when an atom obtains an electron. And as you can see, this increases as we go from left to right across the period.
Another important aspect of chemistry is understanding the order of orbital filling. And I find a really good hint in order to do this is as follows.
Simply draw out all your group numbers 1 to 7 in decreasing order. Next to each of your groups, add an S for the subshell S. Now continue to do so by decreasing by 1 value on each side. Add P, D, and then F. Now include these diagonal lines going across. This lets us know the order of orbital filling. So for example, we would go 1s, 2s, 2p, 3s, 3p, 4s, etc. So if we know the number of electrons in our element, in our atom, then we can easily write out its order of orbital filling. So fluorine, for example, has 9. We know that S's can fill 2, P's can fill 6, and D's can fill 10. So count out 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we would have 1s2, 2s2, 2p5. And that's what we have.
Thank you so much for listening to my quick little talk about chemistry. I really hope you learned something, and I'll talk to you soon. Bye!